Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss the rectangular potential barrier, or we can say it as the tunnel effect. Let's begin. A rectangular potential barrier of height u0 and width 2a is given as the potential is given as 0 in that of region where x is less than minus a and x is greater than plus a, and that potential is u0 in that of region between minus a to plus a. Look at that figure, that is the rectangular potential barrier at x is equal to minus a, at x is equal to plus a, means the width is 2a, and the barrier of height potential, that is the height with the u0, inside that region minus a to plus a, the potential is u0, and in that region and that region the potential value is 0. Here the potential is 0, here also the potential is 0. This one is the region 1, that one be the region 2, that one be the region 3. This is the energy E we provide. Suppose a beam of particles traveling along the positive x axis from left to right, means this way, are incident on the potential barrier u0 in region 1 and 3. In region 1 and 3, the energy of particle is totally kinetic, while in region 2, the energy of that particle both kinetic and partially potential. But if when E is less than u0, means the energy of that particle is less than that of potential barrier, then according to classical view, the probability of reaching the region 3, if a wave or the particle is reaching that of region 3 after crossing that of region 2 is 0. That means there will be no such probability of finding that particle in that of region 3 when that particle is incident in that of region 1. In classical theory, that is the probability of finding that particle in region 3 when it is incident in region 1 and passing through 2 is 0. But in quantum mechanics, however, according to quantum picture, the transmission probability is definite and small, that is non-zero. Means in quantum mechanics there will be some probability of finding that particle when that particle is incident in that of region 1 and passes through that of region 2. There will be some probability of finding that particle in region 3 in quantum mechanics, that is non-zero. That means there will be some possibility to find that of particle in region 3. This type of effect is known as, this type of behavior is known as the tunnel effect. Okay, that is the tunnel effect, means that rectangular potential barrier treat as a tunnel. Let us we mathematically treat two different limitations, that means when E is less than u0, and again another limitations when E is greater than u0. What should be the solutions in these two different conditions? For that of particular mathematical treatment, let we treat for region 1 the wave function associated, let psi 1, and here for region 2 let the wave function associated be psi 2, and for region 3 the wave function is associated in psi 3. Look here, according to that of quantum picture, what happens? The wave travels, passes through this, there will be some probability of finding that particle in that of region 3. Let us treat mathematically. First, solution 1, when E is less than u0, in region 1 and region 2 and region 3, we apply time independent Schrodinger equation. This is the wave function psi 1. Here that is d square psi 1 by dx square plus 2m e minus 0, that is the potential. Potential in first region and third region is 0. Therefore, the equation looks like this, where k square is equal to me divided by h cross square, and its solution in that of form psi 1 is equal to a e to the power ikx plus b e to the power minus ikx. Similarly, for that of region 3 also the potential term will be 0 and the wave function treated as psi 3, and the solution in that of form psi 3 is equal to f e to the power ikx plus g e to the power minus ikx. And in region 2 there will be some potential, and that potential is u naught, where beta square is equal to this much, and the solution in that of form psi 2 is equal to c e to the power beta x plus d e to the power beta x. What are these a e to the power ikx? A e to the power ikx is the wave which has the amplitude a and is travelling along the positive direction of x axis, and b e to the power minus kx is the wave of amplitude b and travelling along the negative direction of x axis, and c e to the power beta x is the exponentially increasing wave of non-oscillatory, that is the disturbance travelling along x axis. And again d e to the power minus beta x is similarly the exponentially decreasing where of non-oscillatory disturbance is travelling along that of x axis, and f e to the power ikx is the transmitted wave in that of region 3. This one is the region 1, that one is region 2, that one is the region 3. And here as the particles are moving from left to right, here the particles are moving from left to right, the boundary condition, so since the particles are moving from left to right, here g is equal to 0, g is equal to 0 as the particles moves from left to right. Therefore, the solution will be in the form psi 3 is equal to f e to the power ikx, that indicates that term has no significant value to that of solution. So, here a, b, c, d and f are the amplitudes. We have to determine the value of these amplitudes by using the corresponding boundary conditions. So, let us introduce that boundary conditions. Boundary conditions: psi 1 at x is equal to minus a is same as that of psi 2 as x is equal to minus a. Look here that figure. At x is equal to minus a, psi 1 is same as that of x is equal to minus a, psi 2 is same. Again its differentiation, that means the slope at x is equal to minus a is same as that of slope x is equal to minus a for that of second wave function psi 2 with the same. This is the first boundary condition, second boundary condition, and the third boundary condition be the psi 2 at x is equal to plus a is same as that of psi 3 at x is equal to plus a, and its corresponding differentiation d psi 2 by dx at x is equal to plus a is same as that of d psi 2 psi 3 by dx x is equal to plus a. Let us use these boundary conditions to that of equations psi 1, psi 2 and psi 3. Let when we use the boundary condition 1 means psi 1 at x is equal to a minus a is equal to psi 2 x is equal to minus a, psi 1 psi 2 as x is equal to minus a, we get a e to the power minus k a plus b e to the power plus I k is equal to c e to the power beta a plus d e to the power minus beta a. Again using the boundary condition b means its differentiation at x is equal to minus a is same as that differentiation at x is equal to minus a. Its differentiation at x is equal to minus a, we get I k whole into a e to the power minus I k plus b e to the power minus I k is equal to beta minus c e to the power beta a plus d e to the power minus beta a. Again using that of boundary condition c psi 2 at x equal to a is equal to psi 3 at x is equal to a, that is c e to the power minus beta a plus d e to the power beta a is equal to f e to the power I k. Again its differentiation, when we use that of third boundary condition we get that equation. Now we have to get a, b, c and f. That is why just adding 1 and 2 then subtracting 2 from 1, adding 1 and 2, 1 and 2 add, get that equation, and then subtracting 2 from 1 we get that equation. Again that result will be added and subtracted simultaneously. Just add this, again adding these two and subtracting. First we add and subtracting these two, then add and subtracting these two. First we add 1 and 2 and subtracting 2 from 1, again adding 3 and 4 and subtracting 3 and 4. We get c and d. Here we get c and d, here also we get c and d. That means we have to equate these 4 equations as far as their terms are concerned. So when we equate the c terms, that is v double I and vi, v double I and vi, we get that equation. Again equating the d terms means v triple I to v, we get that equation. Okay, what we treat? First we take the boundary conditions, and according to our boundary conditions these 4 equations are derived. First 2 equations add and subtract, then last 2 equations add and subtract. Consequently we get the equations d and c. Here you also get c and d. Since c and d we have to equate these equations, we equate c terms, then we equate d terms. Again these 2 equations ix and x, adding and subtracting these 2. When we add ix and x, we get that equation, where we use the hypertrigonometry function. Again subtracting ix from x, subtracting that ix from x, subtracting ix from x, equation, that equation. Further these 2 equations add and subtracted, adding these 2 equations we get f by a is equal to this much. Here just we replace 2 beta a as theta. Again subtracting we get b by f is equal to that much, where we substitute omega is equal to this much, and zeta is equal to that much, and theta is equal to 2 beta a. Okay. What we take? The equations as we find here, equation ix and x added and then subtracted, added and then subtracted, and these two results are again added and subtracted, again added and subtracted. Okay. Finally, from these equations we get f by a, from that equation we get b by f. When we multiply these two, we have b by a is equal to that much. So, the reflection coefficient or reflexivity, that is denoted by r, that is the square of magnitude of b by a. When we take the square of magnitude of b by a, we get that quantity. The transmission coefficient or transmittivity, that is the square of magnitude of f by a. When we take the square of magnitude of f by a, we get that one. The quantity we introduce here, omega and zeta and theta, we prefer omega square, u naught square divided by u naught into e, 1 plus omega square 1 plus the value of omega, and simplifying that term, that is zeta square by 4, zeta square we substitute u naught square divided by 4e, u naught minus e, 1 plus omega square. Therefore, r plus t, reflectivity plus transmittivity, is equal to 1, where r is equal to that much and t is equal to 1, means r plus t is equal to 1. Probability is conserved. Probability is said to be conserved. Okay. This is the first case, the solution 1. Just overlook what we take in that of solution 1. When E is less than E naught, region 1, region 2, region 3, its solutions. Here the significant of G is equal to 0, and psi 1, psi 2 and psi 3 in that of corresponding regions, and these are the amplitude terms A, B, C, D and F. These amplitude terms are evaluated by using that of boundary conditions. We use 4 boundary conditions. Accordingly, the 4 equations are there, and first we add and subtract 1 and 2, then add and subtract 3 and 4. Result, adding 1 and 2, result, subtracting 1 and 2, result. And since C and D are same in these two equations, we equate C and equate D. The equations again Ix and X add and subtracted. We just add and subtracted Ix. We introduce the hyper-Trigonometry function, and subtracting Ix and X, we get that equation. Again these results also add and subtracted. Adding we get f by a, subtracting we get b by f, and multiplying these two equations, b by a is equal to that much. We introduce omega, zeta and theta. What are these values? Then reflection coefficient or reflexivity, that is r, that is magnitude of b by a square. Transmission or transmission coefficient, transmittivity, that is f by a magnitude square. Zeta square 1 plus omega square. Just we treat what should be the its simplified manner to introduce 1 plus omega square, that is that much. Therefore, r plus t is equal to 1. The probability is conserved, r in terms of this and t in terms of this. So, what are the conclusions are done from that of solution 1? We treat as conclusion 1. What are the conclusions? Since r plus t is equal to 1, reflectance plus transmittance is equal to 1, that is the sum of reflection and transmission coefficient is unity, that is the conservation of probability. R plus t is equal to 1 means that is the conservation of probability holds good. Then second conclusion, as E tends to 0 means the energy of that of incident particles is 0, that is t is equal to 1 by 1 plus infinity, so t tends to 0. Hence E tends to 0 means that the transmittance also tends to 0. Hence, the transmission coefficient vanish. It is accordance with that of classical theory. Classical theory means transmittance vanish. As energy increases, the transmission coefficient increases. That is the conclusion number 2. Then conclusion number 3. When t is not equal to 0, here the t tends to 0, but when t is not equal to 0, even if E is less than u naught, E is less than u naught and t is not equal to 0, this shows a contradiction to classical theory. That means the particle has probability of penetration through that of barrier, which is known as the barrier penetration, or that is the tunnel effect, as we introduced in that of quantum theory. When E tends to u naught, we find out the limit at E tends to u naught of that of transmission coefficient t. We get that factor. That factor, that factor is known as the capacity of the barrier, whereas the limit sin s theta is equal to theta, that is 2 beta a, and limit of that reflectance is equal to 1. Last conclusion, for a very wide barrier sense, that is beta a is very greater than 1, so e to the power 2 beta a is very greater than e to the power minus beta a. So that is the sine hypertrigonometry function sin of s theta, that is e theta by 2, that is e to the power 2 beta a divided by 2. That is the transmission coefficient 1 plus this much. This term indicates e to the power minus 4 beta a. That means the transmission probability damped off. We show it graphically, just damped off. The transmission coefficient is damped off. These are the conclusions are made from that of solution 1. To use the solution 1, we get this type of conclusions. So again, there are another limitations, that means solution 2. Introduce solution 2. Solution 2, where E is greater than u naught. E is greater than u naught means the energy of that of incident particles is greater that for barrier potential. Here is the graphical view when energy is greater than that of u naught. Again, we introduce region 1, region 2 and region 3, region 1, region 2 and region 3, and corresponding wave functions are psi 1, psi 2 and psi 3. We use time independent Schrodinger equation and its solution psi 1 this much, and here introduce alpha, a constant alpha square. Again the solution is in that of form, and in region 3 also that of solution. But again there will be no such significant of that of term g, since g is equal to 0. G is equal to 0, therefore psi 3 is equal to f e to the power I k x. In region 1, these are the amplitude terms, a e to the power I k x. Region 2, region 3, at the reflected waves. Introduce that of incident wave, a e to the power I k x, reflected wave psi r, b e to the power minus I k x, and transmitted wave psi 3, third number wave, that is f e to the power I k x. That is the incident, for that of incident wave, the probability current density h plus k by m, magnitude of a square. Similarly, the reflected wave, for that of reflected wave, the probability current density Jr, reflected, for that transmitted wave, this much. Now the reflectance, that is Jr by J in magnitude of B by A, magnitude square, and the transmittance, magnitude of F by A square. We have to prove R plus T is equal to 1. We have to prove. How we prove? Means we have to take the amplitudes B, A, F, and these amplitudes are derived by using proper boundary conditions. Let us introduce the boundary conditions for that of solution 2. Here the boundary conditions, when psi 1 is same as that of psi 2 at x equal minus a, and its differentiation also same. Using boundary condition 1 in that of equation, psi 1, here is the psi 1 and here is the psi 2. Use psi 1 equal to psi 2 at x equal to minus a, we get that one, and using condition 2 in its differentiation also this one. Now adding and subtracting, similar procedures are adopted here. When we add these two, we get c is equal to this much, and when subtracting we get d is equal to that much. Again we introduce another two boundary conditions, psi 2 at x equal to a and psi 3 at x equal to a is same and its differentiation also same. When we use these two boundary conditions in that of corresponding equations, we get c, get that equation, and use boundary condition that of d, we get that equation. Again adding and subtracting these two, we find out the values like c and d, c and d. Here we get c and d, here also we get c and d, means we have to equate these two terms. Now equating these two, now equating these equations, we get first equating c, we get that term, and again equating d, we get these terms. Again the results of v double I and the results of v triple I added and subtracted. When you add v double I and v triple I, we get the result of f by a. Just introduce theta is equal to alpha. Again subtracting v double I and v triple I, or v double I from v triple I from v double I, subtracting, we get b by f. We introduce a new term, that is eta, and multiplying these two, f by a and b by f are multiplied, we get that term, where eta is equal to this much, omega is equal to that much. Just similar procedure as we done in case of solution 1, this is very similar. Therefore the reflection coefficient or reflexivity, that is r, is equal to magnitude of b by a square. Then the transmission coefficient or transmittivity, that t is equal to magnitude of f by a square. For a mathematical purpose we use r plus t is equal to that much, and what is that of eta square, 1 plus eta square, then omega square minus 1, this term is same as that of eta square, so introduce eta square. Eta square is same as omega square minus 1, that is omega square minus 1 is same as the eta square, and cos square theta plus omega square sin square theta is equal to 1 plus eta square sin square theta. Therefore r plus t is equal to 1, means the conservation of probability holds good here. Thus r is equal to, we use its eta square sin square theta divided by this much, omega square minus 1, simplifying that one, and t similarly we get t, and eta square is equal to u naught square 4e minus u naught, where alpha square, k square values are given. We get these values from that of equations here, alpha square and k square values, So r, t are written. Just overlook what we studied in that of solution 2. This is the case when E is greater than u naught. In that of region 3 regions we get 3 solutions, and these solutions are written as psi 1, psi 2 and psi 3. And to show r plus t is equal to 1, we have to get these amplitudes, so the boundary conditions are introduced. Two boundary conditions, two equations, these two equations are added and subtracted. Then two boundary conditions and two equations, these two equations consequently added and subtracted. then we have to equating these 4 equations as far as their terms are concerned. We get another 2 equations, and again these 2 equations are added and subtracted. We get f by a and b by f, and these 2 equations are multiplied with each other. Therefore, the reflectance R and the transmittance T are considered, and R plus T we have to find out, where the introductory term eta square 1 plus eta square omega square minus 1 are derived, and finally putting these values we get R and T. So, what are the conclusions are drawn from this solution 2? So, let us look towards the conclusion term, the conclusion factor. Conclusion for that of solution 2. First point, since R plus T is equal to 1, reflectance plus transmittance is equal to 1, so the total probability is conserved. So, the sum of reflection and transmission coefficient is unity. Since R is not equal to 0, so T is not equal to 0, that is the complete transmission through the barrier is hypothetical without any reflection. The complete transmission through that of barrier means there will be no such complete transmission. The complete transmission is a hypothetical process, or that is the imaginary one. Without any reflection there will be no such transmission, or no complete transmission without reflection. Next, if T is equal to 1, that is sin 2 alpha is equal to 0, therefore its general solution 2 alpha a is equal to n pi, a is equal to n pi by 2 alpha, n pi by 2 alpha term, that is h by 2m e minus u naught. Condition for total transmission, whereas alpha is equal to 2 pi by lambda, that is the phase of the particle, then 2a is equal to n by lambda by 2, that is integral multiplied by lambda by 2, where lambda is the de Broglie wavelength. Total transmission may occur where alpha is equal to 2 pi by lambda. When alpha is equal to 2 pi by lambda means the total transmission occur. Again another conclusion, the variation of transmission coefficient is shown in that figure. We draw in x axis E by u naught and y axis R and T transmittance and reflectance. This is the unity. This is done as, this is the pi, this is 2 pi, that line for that of reflectance, and that line stands for that of transmittance. Where E is tends to u naught, then alpha a is equal to a terms of alpha is very less than 1, and sin alpha a nearly equal to alpha a. So, R is equal to limit 0 and T is equal to minus 1. So, from that of tunnel effect, what are the explanations, or what are the physical explanations we have to explain by using this tunnel effect? The field emission of electron from cloud metallic surface can be explained by this tunnel effect. The dielectric breakdown of insulators, the reverse breakdown of p-n junction diode, the switching action of tunnel diode, and the emission of alpha particles from the radioactive nuclei. These physical phenomena are well described by using this tunnel effect. So, with this video lecture, we understand rectangular potential barrier or the tunnel effect. First, solution 1, when E is less than u naught, use the boundary conditions, 4 boundary conditions, 4 equations. First two equations added and subtracted, and this is the conclusion drawn from that of solution 1. Next, solution 2 is introduced. when E is greater than U naught, as we have done in solution 1, same procedure is adopted in case of solution 2. Boundary conditions are taken into consideration to derive these amplitudes, just adding and subtracting the equations. And finally, the conclusion that is drawn from that of solution 2. And some physical phenomena are well established by using the tunnel effect. So, with this useful and informative notes, let me wind up this session. Thank you.